Okay, what we're going to do today is to learn how Newton discovered his inverse square law of gravitation. Okay, now why are we doing this? Because we can learn a lot through the geometrical thinking, and we see the beauty of geometry and the usefulness of it. Okay, so let's begin. First, I'm going to give some background. All right, the background is that Newton based his laws of gravitation on the discoveries of Kepler. So we're going to talk about the Kepler's law. Now Kepler gave us three laws about the motion of planets around the sun. Now, first, he says that planets go around the sun in an elliptical orbit, right? Elliptical orbit with the sun at one of the focal point, F, and the planet go around it in an elliptical orbit. All right, so that's the first law. Now the second law of Kepler is that the area swept out, right, by the radius vector, right, in other words, by this line F1p, as the planet moves in its orbit, the area swept out in equal time will be equal. For example, if the planet moves from point P to, let's say, point Q over a time of 1 week, all right, this is the area that is being swept out. Then at another position, let's say nearer to the sun, okay, that 1 week will sweep out an equal area, but you can see that it actually covers a longer distance because nearer the sun, the planet will be moving faster. Okay, now, so we can summarize that as equal area, equal time. Alright, that's the second law of Kepler. Now the third law of Kepler says that the period is the time to complete one full cycle. Alright, the period of orbit is related to what we call the semi-major axis. Right? Now, by the way, what is the semi-major axis? If this is the center of the ellipse, the distance from the center to the edge in this way, this is called the semi-major axis. Now the period of the orbit is proportional to the semi-major axis length raised to the power of 3/2. Alright, so these are the three laws of Kepler. Right? And of course, Newton made use of his own law together with these three laws of Kepler to discover the inverse square law. So we all know about Newton's laws of motion, the very famous F equals to ma, right? F equals to ma. Now, what Newton found out was that based on his law, that the acceleration is in the same direction as the gravitational force, because the area swept out, right, the second law, in equal time will be equal. He has come to a conclusion that this force will be directed towards the sun. All right, so we know that the F and therefore A are directed towards the focal point where the sun is. Right, the focal point. Okay, so all this we can see them in many of the textbooks. But what we want to do today is something extra. We want to know how actually Newton made his discovery of the famous inverse square law. We all learn about this inverse square law. Indeed, Newton's inverse square law can be written as that the force of attraction between the sun and the planet is proportional to the mass of the sun and the planet, but inversely proportional to the square of the distance between them. So we can write this law as G, mass of the sun, mass of the planet, divided by r squared. G is what we call the gravitational constant. Mass of the sun, mass of the planet, divided by the square of the distance between them. Now, what we want to do today is to understand how this come about, 1 over r squared law, right? And it is very interesting. So, you see, when we want to discover a law, it's like inventing a cake, right? You have got ingredients, you have got your recipe, then you can bake your cake. Now, the process in which Newton actually discovered his inverse square law is definitely some extraordinary effort. What we have today is we know this cake, right? This is the cake, right? And we'll need some ingredients, and then later on I will show the recipe, right? And we'll see how this cake is actually finally baked. Now, what are the ingredients? The ingredients are some properties of ellipse that he used. Okay, so there are 3 important properties of ellipse. First, okay, let me draw an ellipse first. Okay, and then let's mark down a few important points. Now we know that ellipse has got 2 focal points, F1, let's call it F2, and the center, let's call it O. Right? Now, given a point P, we can draw a tangent to this point P. Right? This is a tangent at the point P. Okay. Now, from the point P, if I join P to O, the center of ellipse, and get to the other side, I can mark another point, let's call it point P prime. Okay, and then from O, if I draw a line that is parallel to this tangent, so I'm going to draw a line parallel to tangent. Alright, I call this point Q, and I call this point Q prime. Alright, now this P prime and Q prime are what we call conjugate diameters. Alright, and there are some very interesting properties. Now, first, if you join a line from F1 to P, alright, join from F1 to P, and let's call this point of intersection between F1 and OQX. The length X to P is equals to, remember our A, semi-major axis, is equals to A. Alright, this is the first property. Okay, by the way, there are 3 properties that I'm going to talk about, and they are each very interesting to prove. Okay, so if you can actually manage to prove them, you'll learn a lot about ellipse. Okay, so I'll leave the proof to you to play around with. The second property of the ellipse that we're going to talk about is that if we join these 4 points, P, Q, P prime, and Q prime, so imagine that I'm going to draw a parallelogram, right? It will be a parallelogram. Alright? The area of this parallelogram, okay, has a very special formula, right? Area of parallelogram, okay, P, Q, P prime, Q prime is equals to 2AB. Now A, we just mentioned, it is the semi-major axis, right? B is what we call the semi-minor axis, and you can guess what is B. If this is A, of course B will be this, right? The semi-minor axis. So the product of A and B is actually half the area of this parallelogram, or the area of this parallelogram is 2 times AB. That's the second property, right? Try to prove it yourself, and you have some fun doing it. Now the last one that we're going to make use of is a ratio, okay? And I'm going to construct some more points, okay? First, if I draw another line, okay, that is going to be parallel to the tangent, also parallel to QQ prime, right? Let's just draw a line, okay? And let's call this point S, okay? And call the intersection here with OPV, okay? And then, yeah, that's good enough. And then take a ratio of FV squared to OQ squared, right? SV squared to OQ squared. That's going to be equal to VP times VP prime over OP squared. Alright, so now we have got the three properties of ellipse, we have got the three laws of Kepler, we are ready to look at Newton's recipe. Okay, so Newton's reasoning. Newton's reasonings. Right. Now I'm going to draw another ellipse, and then we're going to analyze. Now another ellipse, and then we have got our sun at the point F1. Remember that there is another focal point F2. We won't need that too much. F1 is where the sun is. P is where the planet is. Okay, now the planet is going around the sun in a counterclockwise direction. And we are going to imagine a velocity vector at point P. Alright, the velocity vector at point P, I'm going to represent this. Of course, the velocity vector will be along the tangent line at P. Okay. Now, let's also get all our P prime, Q prime out because we'll need them later. So let's construct. So here is a point O. I'm going to draw join P through O to the other side. That's my P prime. I'm going to draw a conjugate diameter that's parallel to my tangent line, remember? And that's my Q prime. Alright? Q prime. Q and O. Okay, and remember this property that from F1 I draw a line to P. I'm going to intersect OQ at X. I need that line also. I'm going to draw a line from F1 to P. That's the line that joins my sun to the planet. And the point X is the point intersection. Okay? Now, the reasoning starts this way. This is the velocity vector, right? If there's no attraction from the sun, according to another law of Newton, the planet would have gone along a straight line and it won't be able to follow the ellipse anymore. But because of the force or the acceleration directed towards the sun, right, we will see this velocity vector make to change direction. All right. So the direction in which this velocity vector is going to change should be in the direction of PF1. You get it? So we're going to construct a vector parallel to PF1, starting at this point, parallel to PF1, so something like this. Can you see that? Right? And we're going to mark 2 points so that it's easier for our derivation later. We're going to call this point R. We're going to call this point S. RS is parallel to PF1. Now, if we draw a parallel line through S to OQ, remember that I'm going to need a parallel line just like what I did here with my SV. This is the parallel line. And I'm going to call this point U and this point V. Now, if you look carefully, you realize that PU and SR, PU and RS, they are parallel and they are equal in length. Right? US and PR are also parallel and they are equal in length. So we have a little parallelogram up there, PRSU. Okay, now we need 2 more points to complete our investigation. First, I'm going to drop from S a perpendicular to F1P. So from S, I'm going to draw a perpendicular down to F1P, and let's give it a name. Let's call it T. All right, let's call it T. Okay, now from P, I'm going to draw another perpendicular line, but this time to OQ. All right, or QQ prime. Okay, and give it a name. Let's call it W. All right, let's just call it W. Okay, I'm done with my picture. All the points are there, and we're ready to use geometry. In particular, the 3 properties of ellipse and Kepler's law. Okay, let's see how we go. Now, first of all, I guess in Newton's mind, he must be looking for this. He knows that the force or the acceleration is directed along F1P. He knows that Rs is proportional, all right? Proportional to the velocity change. Because remember, initial velocity is this direction. Because of acceleration in that direction, this is a change in velocity, all right? So what is in his mind must be that how is this change in velocity, which will be related to the acceleration, related to F1P, the length between F1P and SR. If we can find that relation, SR and F1P, how are they related? We will have, as I said, bake our cake. All right, we have found Newton's law. Now, that requires quite a bit of geometrical thinking. All right, but we'll get there. Now, first of all, let's remind ourselves that Rs is proportional to the change in velocity. Okay. Let's also remind ourselves that from our property here, xp is a. Right? We write that down again, just to emphasize on that, so that later on we can make good use of it. Now, Newton saw 2 sets of similar triangles. They are extremely important. Okay, and see whether you can identify some similar triangles in this drawing. The first similar triangle is between the triangle PUV and PXO. Can you see them? Triangle PUV is similar. Okay, I'm going to use this symbol for similar. All right, similar to triangle PXO. PUV similar to PXO. So from there you can set up some ratio, right? You can see that the ratio PU to PX, yeah, PU to PX will be equals to PV to PO, right? PV to PO. Okay. Now we are trying to get down to the formula that relates Rs with F1P, remember, and we are going to make good use of this number 3 later on. So you are seeing some of this starting to appear. Can you see a PV over there? I also have my PV over there, I also have my PO. Alright? Okay. Now that's the first triangle. Now the second triangle that is similar is STU and PWX. Can you see them? STU and PWX. STU, PWX. So from here, he can set up another ratio. Okay, let's see what we can get. ST to PW is equals to, ST to PW should be equals to SU to PX. Aha! PX. Can you see appearing in both relationship? PX is extremely important. PX is equals to A. Okay, now the puzzle is getting solved pieces by pieces. Now we are going to rewrite some of this ratio with stuff that we know. First of all, PU is equals to RS, right? Up here I didn't write it down, but just now I explained that this is actually a parallelogram. PU is actually equals to RS. So I can actually replace this by RS. Remember, I want to find a relationship between RS and PF1. So it's good to replace PU by RS so that I can use it. And I can replace my PX by A, okay? And my PV and PO later on, most likely I'm going to use it somewhere here. So I'm going to write this as RS equals to A times PV over PO. Okay, I hope you can still see it. Yeah, it's still on the screen. Whoops, not on the screen anymore. So I think I better rewrite it somewhere else. Okay, let me change a little bit. Because there isn't enough space over there. Okay, or maybe I adjust. Okay, a little bit. Where am I? Okay, PU is my RS. So I can write RS equals to PX is A. So it's PV over PO times A. Okay, now the other similar triangles we talked about, let's write that down again. STU and PWX. Alright, and we have got similar triangle ratios. ST to PW equals to ST to PW equals to PU to PX. Right. And how are we going to make use of stuff to get another relationship? Well, we can rewrite SU this time. Wait, where's SU? Oh, sorry, there's a mistake here. Should be SU, huh? Right, ST over PW equals to SU over PX. Yeah, got it right. Okay, we're going to rewrite SU as a subject. So I can write as SU equals to, right, remember PX is A. So it's equals to ST over PW times A. Alright. Okay, maybe we'll put this as equation 1. And this is equation 2. Alright. And ready for us to use. Now, here is another insight from Newton. Can you see the triangle OPQ? Can you see the triangle OPQ? Now the triangle OPQ is actually a quarter of the parallelogram PQ, P prime, Q prime. Can you see? OPQ. Alright, it is a quarter of this whole parallelogram PQ, P prime, Q prime, a quarter of the area occupied by triangle OPQ compared to the whole parallelogram PQ, P prime, Q prime. Now remember the area of the parallelogram is 2AB. So triangle OPQ, alright? So triangle OPQ area is actually a quarter times 2AB, right? Which is half AB. But there's another way to look at triangle OPQ. Because we have dropped a perpendicular down from P to W, can you see? Now, look at this triangle OPQ. This is the height of the triangle. This is the base of the triangle. So this is also equals to half times OQ times PW. This is going to be useful. We'll call this our relation number 3. Okay. We need one last relation before we're going to pop this into the recipe. Okay. So one last relation is actually from Kepler's second law, equal area, equal time. Okay. So if we imagine that this is the sun, this is the planet, and over a certain time it sweeps out an area F1PS. Can you see that? Now, although this is not really a triangle, but I want you to imagine that all these are actually infinitesimally small, right? In other words, I have actually blown it up to facilitate the explanation, all right? But actually, the real vectors are extremely small, so you can imagine that it actually forms nearly a triangle, F1SP. So the triangle F1SP, right? It is, now I'm going to use another symbol. Now when you see this symbol, means that we call it asymptotically approaching. In other words, when your S is so close to P, it is practically equals to what we are doing. So remember the triangle F1PS, that's half times F1P. Aha! I have my F1P coming out. So we have been waiting for it for a long time. We have got our RS hanging around here, right? We hope to find a relationship between RS and F1P. That is the whole aim of this exercise. F1P is the base. What is the height? ST, right? Okay, let's call this relation number 4. We've got 1, 2, 3, and 4. We're ready to put them together. Now, let's write down number 3. SV squared over OQ squared. What would that be? SV squared over OQ squared. Do we have something like that? Well, we don't have, huh? We don't have. But do you see that SV is also asymptotically equals to SU? In other words, if your S is very, very close to P, U and V practically are the same point. Alright? Now this is a little bit hard to accept in the first place, right? But if you think carefully, that's what's happening, right? If S is very close to P, let's not put it here, but put it very close. U and V are practically the same point, isn't it? So I can write this to be asymptotically equals to SU squared over OQ squared. Now SU squared over OQ squared, I think we will have something soon. Why? Because SU squared, we have something up there. Can you see? SU is over here. Alright? OQ can be found from here. Right? So all we have to do is make use of our relation number 1 and number 3. Can you see that? Number 1 sorry, number 2, SU, right? Number 2 and number 3, right? So I'm going to write them down. Is equals to, SU is ST over PW times A squared over, now OQ, now the half, we can actually drop it, all right? Half and half, let's just drop it. OQ is AB over PW. AB over PW. The whole thing squared. Ah, nice. There's a PW and there's another PW. We can actually cancel them out. There's even an A that we can cancel out. So the whole thing actually simplify to just what? Oh, okay. Let's just save one more line by giving some name to some of this area, which we know is a constant. Okay, this area F1SP, right? We know it's a constant area because for a constant time we are going to sweep out a constant area, right? Let's call this area H over 2, right? Okay, so H over 2 equals to half F1P ST, and therefore ST is H over F1P. Can you see that? Wow, I got my F1P. Most important is to get the F1P coming out. Right, so let's simplify now. PW and PW cancels, A and A cancels. ST can be replaced by H over F1P. Okay, so simplifying everything, I get H squared over, now the B still remains, so B squared and F1P. I need my F1P to appear, and the nice thing is that F1P square is appearing. Can you see the inverse square? Law is coming to shape. Alright, the cake is nearly baked. Okay, now this is the left hand side. Now let's work on the right hand side. Okay, so right hand side, VP, now I'm going to write it as VP over OP times VP prime over OP. Right, it's the same thing actually. Huh? OP squared is OP times OP. VP over OP times VP prime over OP. Now where can I get my VP over OP? Aha, here. Can you see that? PV over PO is the same as VP over OP. And my RS is coming up. Right, so on one side I have my RS, one side I've got my F1P. The relationship is nearly there. But there is another asymptotically equal thing that I need. What is it? You see, so far I haven't got VP prime over OP. I haven't got any VP prime over OP. But where's VP prime? This is VP prime. Now, can you imagine that if this S is so close to P that V is going to shift very close to P, VP prime is practically 2OP. VP prime is practically 2OP. Okay, again, this you may not be accepting it on first sight, but think about the motion very, very close, S very close to P. You will see it. Okay, so VP over OP, let's see. VP over OP is RS over A. Let's write that down. RS over A. VP prime over OP, as we say asymptotically, that's twice of OP. So I can write as times 2. Now I can equate. This is my left hand side. This is my right hand side of my third property of my ellipse. If I equate them, where is the law of Newton? Now we can make RS the subject. So RS will be equals to H squared RS A over 2B squared times 1 over F1P squared. This is Newton's inverse square law of gravitation. We have finally got it. Okay? And I hope you really appreciate the effort, right, the genius of Newton in his discovery of his inverse square law. Thank you.